So hi everyone. Today I'm going to be explaining the solution to one of the problems from the last lunchtime, which is permutation split. And I'm Radoslav. You can see like a slide about me. And I guess I'm just going to go first to the problem statement, then to the solution. If you have some questions, just ask them during the session. And yeah, also after the session, please fill out the feedback form, as it's very helpful. And yeah, I guess let's just get started. So first I'm going to go to the problem statement and just quickly go through it. Basically, the question is relatively simple in terms of problem statement. And we are basically given a sequence, which is A1, A2. We are given a permutation. The permutation is just like reordering of the numbers from 1 to n. And we want to split it into two subsequences such that the number of inversions in the first subsequence is equal to the number of inversions in the second subsequence. And basically, like these two subsequences should be disjoint, and every element should appear exactly once. Or in other words, we basically have a sequence, which is a permutation, like this is the initial sequence, and we want to partition it into two parts such that the number of inversions in the first part is equal to the number of inversions in the second part. And for those who aren't familiar with inversions, it's just the number of pairs ij, such that I is less than j, and ai is greater than aj. So in other words, like basically, yeah, I mean, I'm pretty sure most of you are familiar with what inversions are. And the constraints are basically n is less than 100, which kind of suggests that we want a cubic solution, because that's the normal constraint that's required when we have basically a cubic solution. So actually, there are two ways to approach this problem. And I'm going to try explaining a solution where we kind of generalize the whole problem to graphs. As in a way, the approach for graphs is pretty cool. And you can actually basically reduce some other problems to this graph problem. But yeah, I guess let's just get straight to the solution. I'm going to be using one node with some nodes. So yeah, again, as a recap, we basically have a sequence or like a permutation. I'm going to call it A1 to AN. It's basically the same as P1 to Pn. But yeah, we want to split it into two sequences such that every element is in exactly one sequence, such that the number of inversions is the same in both sequences. And by number, I'll just when you see like the hashtag inversions, I'm just using hashtag as the number. I guess that's just to let you know if you are kind of confused by the nodes. And yeah, here, like again, we are kind of expecting a cubic solution because we have n less than or equal to 100. So yeah, basically, as I said, I'm basically gonna convert the problem to graph theory, because this way it's gonna be more general. And if you in the future just get a problem which can be reduced to the graph version of this problem, you will know the solution. And like the reduction is actually very simple. We are just going to have the positions, or like the elements of the permutation, being vertices, and then the inversions will be the edges. And I mean, like we have n is relatively small, so we can just literally fix every two positions and check whether this is an inversion. And if it's an inversion, we basically add an edge. So in other words, we'll have a graph where we have vertices for every position, and then we have edges for every inversion. So then the sequences, or like the two subsequences, in some sense will be subgraphs. And like let's basically recap what our problem will be now. If it was like a graph theory problem, we basically are given a graph G, which is defined by V, which is like the vertices, which are the positions, and E, like the edges, which will be the inversions. And we want to split the vertices into two sets, V1 and V2, because like in a way, the subgraphs are defined by the vertices in them. And like the constraints for V1 and V2 will be that the union on V1 and V2 is basically V, or in other words, like every vertex appears in either V1 or V2. And then the second constraint is basically the size of the set of edges such that both of their endpoints. So yeah, basically we go through all edges, and if both of their endpoints are in V1, this will be like the set of edges in the first subgraph, and then the set of edges in the second subgraph. Or in other words, because like the edges are the inversions, the first thing here, like the second criteria is basically number of inversions in V1 is equal to number of inversions in V2. But like this is like a written with like some set theory, like very basic set theory. Or in other words, we just want the number of edges that have both of their endpoints in V1 to be the same as the number of edges that have both of their endpoints in V2. So yeah, basically we want, in some sense, like there's a drawing, like if we have like this graph, we want to basically pick a subset of vertices. For example, like two subsets of vertices, such that every vertex will be in either the first one or the second one. And the number of edges which are in the first one will be the same as the number of edges in the second one. Or like here, you can see that we have 4 edges in the green one and like 4 edges in the red one. So like this is like a fine split of the whole thing. You can note that there are 2 edges which are basically not included because they're like cross edges in some sense. And like, I mean, we want the number of inversions inside of the first set to be equal to the number of inversions in the second set. So that's why we basically want the number of edges which are either in the first, fully in the first subgraph or fully in the second subgraph. But yeah, also I have to note here that it's not necessarily that that these subgraphs will be fully connected. Because for example, imagine this bipartite graph, and we can just easily choose the left side as one of the sets and then the right side as the other set. And like if this graph is something like that, then again it's fine to basically, I mean, basically for this example, we have 0 edges in the first set and 0 edges in the second set. Or in other words, we just can split into subsequences such that there are no inversions in them. But yeah, what I want to say is that when we are choosing these 2 sets, V1 and V2, it's not necessarily that they'll be basically connected, although like they may be connected. But yeah, like this is the first observation which we are going to use as, in a way, like when you think of something general, it's sometimes easier to approach the whole problem. And I mean, generalizations are pretty cool because if you have some other problem, you can reduce it to this generalization, which you already know how to solve. So yeah, I mean, it's pretty cool. So I guess let's continue with the solution. All right, we're going to start with some basically observations. So the first observations which we are going to use is slightly related to this cross edges. But like, I mean, partially, let's first actually look at all of the edges in our graph and define 3 types for them. The first one will be basically the edges which are fully inside V1. Or in other words, like both of their endpoints will be in V1. Or this is basically the number of inversions. If we talk about like the permutation split problem, this is basically the number of inversions in the first subsequence. Then the second type of edges is basically they're fully inside of V2, or like they have both of their endpoints in V2. And yeah, that's, in other words, the number of inversions in the second subset, in the second subsequence. And what we want to, I mean, basically what the problem asks us is to check whether we can split the vertices into 2 sets such that the number of edges of type 1 is equal to the number of edges of type 2. However, again, we have like some edges which are of the third type, or like they're cross edges. And like cross edges, as you could have guessed, are all other edges. Or in other words, like they have one of their endpoints in the first set and like the other endpoint in the second set. Or like in this example, like with the bipartite graph, all of the edges are basically cross edges because, I mean, so okay, yeah, I had to mention that we'll define all of these types for some fixed V1 and V2. But yeah, like if we have a bipartite graph, we basically have like all of the edges being cross edges. Similarly here, we just have like these 2 edges being cross edges. Okay, so I guess let's continue with the next observation, which is in a way one of the most important things you would have to use in this problem. And it's basically the observation is that every cross edge will actually appear exactly once in V1 and V2. This may be kind of weird, so I'm going to show a small example after that. But it's pretty useful because this means, all right, every cross edge, right? I mean, we are basically want to check whether we can partition the vertices to V1 and V2 such that the inside of, the vertices, the edges of type 1 should be equal to the edges of type 2. And like we are basically ignoring the edges of type 3. And I mean, in general, that's kind of annoying because we basically have a type of edge which we just have to completely avoid and somehow like enforce that every edge should be counted either as an edge of type 1 or as an edge of type 2. But like fortunately, each cross edge will actually appear in both V1 and V2. So this means that we can actually count it in both V1 and V2. Because like if each of these edges appears like exactly 1 in both of the sets, we can just like, I mean, those edges won't really matter if we also include them, because we basically have each of these edges exactly in the first sum and the second sum. And the problem won't really change if we also include them. So let me just show you a small example of what I mean. Basically, like imagine we have chosen the vertices as follows. So we have like these two and these three, like the red ones, as the first set and the green one as the second one. So this way, like we have 3 red edges and 3 green edges. And also like there are 2 cross edges, which you can see in orange here. And the main idea is that, okay, for the red, each of those orange edges will be counted exactly once in the red set and basically in the green set. Because, I mean, each of these edges has 2 endpoints. One of the endpoints is in the first set, and the other one is in the other set. So, of course, it will be counted like exactly once. And that's pretty useful because now we can actually, basically we have almost solved the problem actually, which is pretty cool. But we need one more observation. So, I mean, in a way, I suppose you can kind of guess here that we try to get some statistic for every vertex that won't really change depending on the choice of V1 and V2. And actually, like, there is such a statistic, and it's here I'm gonna spoil it, and it will be like the degree of every vertex. But like, let's just wait for a bit and like continue with the next observation, which is basically that instead of actually counting the number of edges inside, which are fully inside of V1 and fully inside of V2, let's just multiply the 2 quantities. Or in other words, like, okay, so basically what we want to find is such a choice for V1 and V2, such that the edges that are fully inside of V1, like the number of edges, I'm using like the hashtag for number. So yeah, basically we want to find such a choice of V1 such that the number of edges fully inside of V1 is equal to the number of edges that are fully inside of V2. And basically, this means that we can just multiply by 2 both sides, and it will still be fine because it's just a constant multiplied for 2 sides. So basically, like we will have like 2 multiplied by the edges. I mean, we basically want the following equation to hold, like 2 multiplied by the number of edges in V1 is equal to 2 multiplied by the number of edges in V2. And this is actually quite useful because this way I mean, right now we basically didn't change almost anything apart from this constant 2, which is still fine. But if we think about it, this means that we just want to count every edge twice. And now we actually will go and see what will happen now. Let's have a recap. That's like the second recap. And yeah, let's look what happened so far. We basically split into 2 subgraphs, which was basically that's what we want to see. And I mean, like, the solution will basically be true if we can split into subgraphs. So from the second observation, we actually saw that we can just include the cross edges. And now we just count the inside edges twice, because we saw that for the edges that are fully inside, this constant of 2 didn't really matter. So we can just count each edge that's inside twice. So basically, like using those observations, we see that the count is like we want. I mean, let's see what edges we actually count. For every edge that's inside, like either fully inside of V1 or V2, we count it twice. And every cross edge is actually counted exactly once. And let's like think of what the total count represents. Basically, it will represent the sum of the degrees in the current V. I mean, either in V1 or V2. And like, let's go back to the example and convince ourselves that that's indeed the case. So yeah, basically, let's look at the degrees of this thing. I'm going to just draw them near the vertices. So this vertex has degree 1. This vertex has degree 3, like the total degree. Then this vertex has degree 1 again. This one has 4. Then this one has 1. This one has 2. This one has 1. And like this one has again 2, and this one has 1. So right now we have basically converted our problem to checking whether we can choose the vertices in such a way that the degrees of V1 and V2 will be basically the same. I mean, the sum of the degrees of the vertices. And you can convince yourselves that here, let's first look at the red sum of degrees. Okay, yeah, I'm very bad at drawing on the touch bar, but like it happens, I guess. Some of you already, so yeah, this should be like the red. I'm just gonna erase it, sorry about it. So yeah, let's have like red and then green. So the sum of the green degrees is 1 plus 2, 3 plus 4, 7 plus 1, that's 8. And for the red, I mean, we already know that this is a valid split, and we know that it will be 8, but let's just convince ourselves it's 1 plus 3, 4 plus 1, 5 plus 3, it's also 8. So in other words, we can actually split into 2 sets such that the number of edges in each of the sets is equal, if and only if we can choose a set of vertices that the degree. So that, I mean, like basically, we found a bijection from the number of edges to the sum of degrees. As like what those observations basically suggest is that we can only split when the sum of the degrees is equal in the 2 sets. And that's good because like the degree doesn't really change depending on the other vertices. I mean, like we are basically going to either, I mean, just the degree is just like a pretty cool thing because it doesn't really change. So there's a question. So let me just quickly see what it is. Okay, so there was like a question, what is 12(3)? I'm not quite sure I get what you mean. What is 1, 2, 3? Okay, I guess you mean, do you mean like as the degrees here? So those are the degrees, or basically the number of adjacent vertices. I think you got that, you got this, but like the ones and threes, I'm not exactly sure what you're asking for. So maybe can you give like some more details? But yeah, like I mean, like the 1 to 3 is probably the degrees or like the number of adjacent vertices. And yeah, like degree is, so yeah, maybe like I'll just write it here if, okay, cool. Fair enough. But like, yeah, it's probably good to write it here, but the degree is the number of adjacent vertices. I can't really write it with my touch bar because it's pretty hard. But like degree is defined for one vertex, and it's the number of other vertices that are connected by like just one edge. I mean, in other words, like the number of neighbors. So yeah, going back, basically right now, just to recap again, we have basically converted our problem a bit to actually finding two sets such that the sum of degrees for each of those sets is actually the same. So yeah, let's go back to it. And like, we basically found the recap. We want to split into two sets, and the degrees for each one of them, like the sum of degrees, should be the same. And actually, let's just write this down as a formula and see what we want to do. So as we want to find two sets V1 and V2, such that their union is equal to V, or like basically we want every element to be in either the first set or the second set, we can just define one of the sets as S, and the other one will be just V minus S, like basically all elements that aren't included in S. And what we want to find is basically where we can choose a set S such that the sum of the degrees of X, where X is in set, in like this set S, this should like this sum should be equal to the sum of X such that V isn't in S. I mean, like, so basically, this sum should be equal to the sum of degrees for all X that aren't in S, or like just all X's that are in V without S. Or in other words, like V1 will be equal to S. Like if V1 is equal to S, then of course V2 will be equal just to V minus S. I mean, yeah, this sign is also a minus if you're not familiar with set theory. Or like if we actually try rearranging this thing, because like, okay, we want to choose two such sets, but you can notice that every vertex actually will appear in either the left side or the right side. So we actually know what this should be equal to. Because like, I mean, we want to find two numbers such that, I mean, basically like each vertex will either be in the left side or the right side. And we want like, with this choice of S, the two sums to be like basically equal. So in other words, we can just find the sum of all degrees and like just do 1/2 multiplied by that. As I mean, like if we basically like the sum of the degrees in S is actually fixed, and it's equal to 1/2 multiplied by the sum of the degrees. And the cool thing is that this sum here is actually a constant, because basically like we just go through all vertices, we know their degrees, and yeah, we can find this, and it's a constant. And actually, like this constant is actually equal to E, or like the number of edges, because every edge is actually either in the left side, or I mean, every edge will be in 2 degrees. I mean, like, think about every edge, and it has 2 endpoints. So it adds 1 to 2 degrees. So in other words, like if we have 1/2 multiplied by the sum of all degrees, we have 1/2 multiplied by 2 multiplied by the number of edges. And we can just, the 2 2's actually cancel out. And this means that we actually want to find a set S such that the sum of the degrees in it will be equal to E. So yeah, actually, you can probably already guess that that's a pretty, like much simpler problem, because we just have like, if we just find the degrees, we know the number of edges. We just want to find whether there is a set of like we basically have a set of numbers, which will be the degrees. And we just want to find whether there is a subset with some E, like the number of edges. Again, to remind you, the problem was related to permutations and inversions. So here E is actually the number of inversions. And the degree is basically the number of inversions. Basically, the degree of some position will be the number of inversions in which it exists. So yeah, actually, now it's a relatively simple problem. And probably the more experienced participants already like realized what we'll do after this point. And yeah, let's just quickly recap what the solution would be. I mean, I have skipped one of the final parts, which is actually pretty easy. And what we actually have to do is basically, we first construct the graph, which is pretty easy. After that, we basically extract the degrees. And let's have like some vector degree of, let me just have this closer. So yeah, basically, we first construct the graph, which is very easy. After that, we extract the degrees, which is, again, just a single loop. And finally, we just need to check whether there is a subset in degrees with sum be equal to the number of degrees, with the sum equal to the number of edges. And here we actually use the subset sum, the DP. And yeah, that's like just a standard problem, which is basically we have a set, check whether there is a subset with a certain sum. And I mean, it's a very simple DP. And yeah, I guess like basically this is the solution. And I mean, the important observations are basically how to count the edges. And I mean, like the interesting part of this problem is to basically convert from number of edges inside of a certain component to sum of degrees. And it's actually a pretty useful trick. It's sometimes used in some harder problems related to flows, where you basically want to find something. And yeah, in general, like some harder problems with graphs can actually be, I mean, like, for example, that's very abstract. Actually, so that's the thing. So far I have been explaining this for just a general graph, which is like undirected, but like also it's correct for directed graphs, because so sorry, I just read the question and I completely forgot to mention that right now I'm answering the question. The question is basically, so will this be a directed graph? Okay, so far I have actually been explaining this, how this will work for undirected graphs, but yeah, I mean, in general, it will also work for directed graphs. And yeah, it's pretty neat, because like in some sense, you can think of undirected graphs as directed graphs with just two edges in both directions. So yeah, like, I mean, whichever way you choose, because like both of them work. Not sure whether this answered the question. But yeah, like in general, it's just subset sums. And like finally, we basically have the part which is the complexity. So I mean, the number of edges is basically equal to the number of inversions. And that's basically O n squared, because I mean, worst case, we can just have like around n squared inversions. And then like the length of the degrees is obviously equal to n, or like it's O of n, because we just have degree for every position or every vertex. So yeah, basically we have On from there. So in other words, like the subset sum will be equal to n squared multiplied by n. So it's like a cubic solution. Or it will be equal to n cubed over w, where w is the word size, which is like 42 or 64. Or in other words, like we can use a bit set for this thing, and we can actually reduce the complexity. So in general, this is the solution. And honestly, like the whole problem, which is the reduction to like the graph thing, is pretty cool. And I mean, I think I have seen it before in some local contest. But like in general, it's a pretty cool thing, because maybe you'll reduce some problem to, like in the future, maybe you'll have some problem and you'll be able to reduce it to basically having some graph and trying to find a way to split it into two subgraphs, such that the number of edges in the first graph is equal to the number of edges in the second graph. And like now you will know that this thing is basically solved by having just it's basically solved by just having subset sums on the degrees. And yeah, basically the steps again are you split. So yeah, you include the cross edges and you count the other edges twice. And this way you basically convert your problem to basically finding the degree. I mean, you basically convert the total number of edges into sum of degrees. And that's pretty neat. So yeah, this was way shorter than the previous one. Maybe I'm going to just quickly code the whole solution and submit it, because I mean, the whole tutorial was 40 minutes. But like, I guess you can just ask some questions about it, because if some of the parts were unclear, I can like clarify them. But also I can, right now I'm probably just going to quickly implement it. And yeah, if you have some questions, just leave them in the chat box. And I'm just going to start with quickly implementing the whole solution. And yeah, I'm just going to be answering questions and like commenting about the implementation. So okay, like, haven't really used Sublime Text a lot, but it should be fine. So let's. So yeah, I mean, like, okay. Basically, let's start with the implementation, and yeah, let's have this. Just to note, again, if you have some questions, feel free to ask them. So yeah, basically, let's just start. So okay, let me just quickly see whether. So okay, there was a question about whether it can be solved in ON. I mean, I don't know of a solution which is linear in time, but I mean, I kind of doubt it because just finding the number of inversions is normally done in n log. So if there's a solution, most likely it will be worse than n log. So yeah, I feel like it's not possible. Well, if we are talking about n squared or something better than n cubed, it may be possible, but like for the general case, which is to try to split into sets with the same sum, it's basic. I mean, you know that the number of edges is basically around n squared. So in other words, like, I mean, I feel like the best solution would be nm multiplied by over 64 or over 32, because in general, like the subset sum problem is pretty hard, and yeah, it doesn't really have a lot of better solutions than just the basic DP. So yeah, like I feel like there is no solution which is linear, but yeah, maybe if you find one, it will be pretty cool. So yeah, going back to the implementation, let's just quickly see how the tests were given. So we basically have a test, and then we have n, and finally the permutation. So yeah, basically we have int t. So yeah, let's basically just have the test, and here we have like read, and then solve. So the read is just simple. We have, wow, we have n, which is the number of positions, and then we have like the permutation. So yeah, let's define max n, which will be, I think it was 100. Yeah, let's just say 1 to the 7th power, which is like 128. So okay, let's input everything. Yeah, it was p of I. Now let's have like the degrees. I'm just going to have them in an array. What we basically do is we go through all positions. And now first let's set the degree to 0 because we have multiple tests. We now fix the arrow position. I mean, the positions are basically the vertices, and the degrees are basically, I mean, and the inversions are basically the. So yeah, the positions are basically the positions are basically the vertices, and the edges are basically the inverses, the inversions. So yeah, I guess like let's first have a loop which will set the degrees to 0, and after that we will just find all inversions, which we can do with just a quadratic loop. We fix I, then we fix j. So j will be after I. And now this will be an inversion if and only if P of I is greater than P of J. And if that's the case, we increase the degree of I because we have basically an edge from I to J. So we increase the degree of I by 1. And we also increase the degree of J by 1. And like, let's have the number of edges, which is equal to 0 initially. And also here we have an edge. So we've just increased the number of edges by 1. Let's just have plus plus. It's prettier. So now let's just have a bit set. So basically right now we need to check whether there is a subset with some equal to number of edges, because like it's 1/2 multiplied by the sum of the degrees. We basically showed it. And we'll do this with bit set, and like, because I think that's the clearest way to do it. So yeah, I'm just going to define it globally here. Yeah, actually, let's just define it here. So we have like bit set of max n multiplied by max n. That's, here we have like the max n squared because, I mean, the number of edges will be at most n squared. I mean, it's actually even less. It's actually n choose 2. But yeah, it's definitely less than max n squared. So yeah, this will be like the dp. And initially dp of 0 is equal to 1. So yeah, now we simply go for all degrees. So now we fix every position. And we'll just do dp is equal to dp, or as we can either just use the previous dp, or we can also include the current degree. So it's like dp is equal to dp, or dp shifted with degree of I. So yeah, that's actually, this is just subset sums for the people who aren't familiar with it. That's like the bitmax solution. And this will work in M, which is like the total sum multiplied by n over 64, or like over W, as W is where W is the word size. So yeah, basically now we will basically output yes if dp of number of edges is equal to 0 to 1, then we actually have such a set. So we basically print yes. Otherwise, we basically print no. So yeah, this is basically it. So yeah, I'm just gonna save it quickly and let's just compile it. So it should be here, and it's a.c++. Yeah, I'm just going to compile it and test it on the sample just to be sure that it works. So it's yes, no, which is the expected output. So yeah, let's just copy the solution and submit it. So submit practice. And yeah, let's submit it. Although I'm pretty sure it will work. But yeah, like overall, I think the trick is pretty cool, where you basically convert the number of edges to the sum of degrees. And yeah, I hope like you enjoyed the problem. As you see, it's like accepted. And yeah, if you have some other questions, feel free to ask. I'll be here for a bit, I guess. And again, as I mentioned in the beginning, please fill out the feedback form, because it's very helpful to actually understand what we can improve. So yeah, I'll definitely appreciate it a lot. So yeah, thanks for watching. And I'm going to be waiting for some questions. Let me open the YouTube. Mm. So okay, I mean, like, basically right now I'm looking at the chat in YouTube, and yeah, if you have some questions, basically just ask. So actually, there was a very nice question that was asked. I mean, there's probably your hill. So yeah, basically the question is, what would have happened if we actually also needed to output the two sequences? And yeah, what we would do is actually, okay, let me again go to the solution, because I feel like it's just some implementation details. And the whole idea is that we will actually do backtracking on the DPs. So the first thing is that we actually can't just have like DP as a single. I mean, right now, in a way, we are just keeping the first, I mean, just one column of the DP. So that's why we are basically going to convert this thing to like an array. And here we have like DP of 0, 0 is equal to 1. And like, let's have DP of I plus 1 is equal to DP of I. I mean, basically, we'll just save our answers, like the bit sets, because this is quite useful now, as we can actually go back. All right, so I mean, we actually need to print it only if the answer is yes. So we basically, here in the yes, when we have a yes, we'll see how exactly we'll print this. And the first thing here is we also need to see that here we need to look at dpn and number of edges, and not only the, I mean, yeah, like here we added an additional dimension, so we have to slightly change this. And basically what we are going to do here is we are going to go back and look at the DP values. So in other words, like, let's have like a vector which is v1, because like, I mean, if we find one of the sequences, we know the other one is just all of the other elements. And like, okay, I'm just going to save one of the sequences as it's basically the same. And we are going to go from back. And what we are basically going to do is, yeah, let's also have like the current sum, which is initially number of edges. Because as I said, we basically go back. And also we have like, actually this will be enough. So yeah, we start with I, which is like the first dimension, and the current sum is basically the second dimension. We basically have like, we start from I equal to n, and actually I equal to n minus 1, I is greater or equal to 0, and I minus 1 minus. And now we basically need to check if we need to include degree of I. And what we can do is basically check if dp of, so the first thing is we want, as we don't want to like touch any negative values, we'll basically check if the current sum is greater or equal to the degree of I. Because if that's not the case, we can't really include the current degree. And maybe here it's good to note that we are going to keep the invariant that dp of I plus 1 current sum is equal to 1. As I mean, initially we have dp of n and current sum equal to number of edges. So it's pretty easy. So basically here we have like this if, that, and now we also need to check whether we can actually include this. And to check it, as we are going back, we can actually use the dp. So we need to check if dp of I, which is the current position, and the current sum minus the degree of I is equal to 1. And if that's the case, we can actually just decrease the current sum by this degree, and also we can just add to v1 the current position I. So yeah, and here now v1 will actually just, yeah, v1 will contain one of the sequences. So I mean, like normally when you have some DP and you want to like recover the answer, you just keep the answers, and the easiest way is to just go back and use this DP to like actually check. So yeah, like in some sense, if you do the DP top up, you'll extract the answer bottom down, bottom up. Like you basically do this in the opposite direction, and it's pretty easy. So yeah, basically it's just this thing. So yeah, I guess that's it. And yeah, if you have some other questions, feel free to ask. Okay, cool. So, all right, there was a question which is whether the complexity will remain the same. And the answer is yes, because the only thing that we change is actually the memory complexity, because we only check whether, I mean, like the only major change is that here we actually copy the DP every time. And I mean, this is basically just n times more memory, but like the time complexity won't really change. And the memory complexity is still fine because it's just n cubed. But yeah, like, I mean, the extraction is actually linear because we just have one loop, and inside of it, we just have one if. So yeah, I think this answers your question. And yeah, in general, like if there are no other questions, I guess we can end the session here. Thanks a lot for watching. And yeah, like if you have some questions, you can like message me, and I'm probably gonna answer. Like, so yeah. Also, again, if it will be very helpful if you fill out the survey form or like the feedback form, because it definitely helps. Okay, it seems that there are no other questions. So yeah, let's end it here. Thanks again, and I guess see you next time.